Welcome to The Explainer. Today we're throwing three Titan data structures into the ring for a showdown. They're all battling to solve one of the most common problems you'll ever face in programming, the range query.
Okay, let's get right into it. Picture this. You've got millions of queries hitting a huge array, and you need answers, like now. How do you do it? Think about an analytics dashboard, trying to calculate sums over date ranges on the fly, or a game leaderboard that needs the max score in the top 100. This is that classic range query challenge, and if you get it wrong, well, you're looking at a super slow, frustrating app for your users.
So, what are we really talking about here? The range query problem. It sounds fancy, but it's actually pretty straightforward. You've got an array of data, right? And you just need to ask questions about any piece, any range of that array. Questions like, hey, what's the sum of elements 10 through 50? Or, find me the minimum value from index 100 to 200. The trick is you have to do it fast. Like really, really fast, over and over again.
All right, so to solve this exact problem, three powerhouse data structures are stepping into the ring. Each one has its own unique strengths, its own weaknesses. So let's meet our contenders for the range query crown.
First up in the ring is the segment tree. You can think of this one as the flexible all-rounder, kind of like the decathlete of data structures. It's a complete binary tree, and it's fantastic at handling all sorts of operations. Sum, min, max, you name it. But here's its real superpower. It can handle both fast queries and fast updates to individual elements. Next up, we have the Fenwick tree, which you might also hear called a binary index tree. This is our lightweight specialist, it's super space efficient, and honestly, a lot of people find it simpler to code. Its whole game is being optimized for problems you can solve with prefix sums, so for range sum queries, it's often the go-to choice.
And our final contender. This is the sparse table. The static speed demon. This thing is the undisputed speed king of the group. It works by doing a ton of work up front, pre-calculating all the answers it can. Why? So that when query time comes, boom, it delivers results in constant time. But, yeah, that incredible speed, it comes with a pretty big catch.
Okay, so how do they actually pull this off? What's the magic behind the curtain? Let's take a look under the hood and see how each one works.
So, the segment tree, it's all about this balanced binary tree structure. The original array elements, they're the leaves, way down at the bottom. And then each node above them, each parent, stores a summary of its children, like their sum or their minimum. So when you need to query a range, you don't have to touch every single element. Nope, you just grab the few nodes higher up that perfectly cover the range you want and combine their summaries. It's a really clever and efficient way to do things.
Now, the Fenwick tree is different. It's less of a tree you can draw out and more like a ladder of buckets for prefix sums. It uses this really cool bit manipulation trick with the least significant bit to figure out how big of a range each bucket is responsible for. So when you need to answer a query, you just climb down the ladder, adding up the values in the right buckets. It's super clever.
And then we have the sparse table. Its all strategy is just pre-compute everything. It builds this massive table of answers. See, row k in the table stores the answers for all blocks of length 2 to the power of k. So when you ask for a query, it just finds two overlapping blocks from this table that perfectly cover your range, combines them, and gives you an instant answer. All the hard work is done up front.
All right, let's get to the main event, performance and trade-offs. We've seen how they work, but how do they really stack up head-to-head? This is the tail of the tape, and it's where you'll figure out which one you should actually use. Okay, this table right here, this is the whole story. Look at the segment tree and Fenwick tree. They're perfectly balanced, right? Log n for queries, log n for updates, and a nice lean O(n) for space. But then, look at the sparse table. O(1) query time. That's incredible, but the trade-offs are huge. Updates? Not supported. Space? It takes up a lot more, O(n) log n. And that little asterisk is key. That O(1) speed only works for certain kinds of operations. So that ov log n time? That's really the sweet spot when your data is dynamic, when it's changing all the time. If you need to do frequent point updates, you need a structure that can handle that just as fast as it handles queries. And that's exactly what both the segment and Fenwick trees give you, that perfectly respectable, balanced performance.
But let's be real, O of 1 is the holy grail. It means your query time is constant. It doesn't matter if your array has 1,000 elements or 1,000,000,000, the answer comes back instantly. So if your data never changes and your operation is idempotent, like min or max, we're doing it twice the same as doing it once, then the sparse table is just unbeatable. Nothing is faster.
But that speed comes at a price,
And that price is space. The whole reason the sparse table is so fast is because it stores all those pre-computed answers, and that leads to its O(n) log n space complexity. Compared to the nice O(n) of the other two, it can be a real memory hog.
This brings us to a classic interview question, maybe even a trap. An interviewer might say, the sparse table is so fast for queries. Can you update it? They're testing if you understand the core trade-off.
And the answer is a hard no. It's a static-only structure. Remember, its whole strategy is built on that pre-computation. Change one value and you might have to recalculate a huge chunk of the table. The only real way to update it is to throw the whole thing out and rebuild it from scratch. A super slow process.
All right, here's another one they love to ask. The Fennec tree is so light and elegant. Can you use it for range minimum queries? Generally, no. The classic Fenwick tree just isn't built for that. Its whole magic trick relies on operations where you can find a range by subtracting two prefixes. That works great for sums, but for minimums, it completely falls apart. I mean, think about it. The minimum of the first 10 elements has nothing to do with the minimum of the first 5 when you're trying to find the minimum of elements 6 through 10. It just doesn't work.
Okay, so we've got all these trade-offs, all these details. So when you're faced with a range query problem in the wild, how do you actually choose the right tool for the job?
Here's a simple decision flowchart for you. First question, is your data static? Is it never going to change? If the answer is yes, you should be thinking sparse table. Second question, is the operation idempotent, like min, max, or GCD? If yes again, the sparse table is your O(n) winner, hands down. But if you do need frequent updates, then you're looking at the other two. Is it a straightforward prefix sum problem? Go for the Fenwick tree. It's simpler and more efficient. For pretty much anything else that needs updates, the segment tree is your safe, flexible bet.
And let's just boil it down to an interview cheat sheet. Range sum with updates. Fennec tree or segment tree. Fennec is usually easier. Range min/max with updates. It's got to be the segment tree. Static range min/max/GCD. Sparse table, no question. And if they hit you with a real curveball, like updating an entire range of values at once, well, that's when you bring out the big guns, a segment tree with lazy propagation. That's a more advanced topic, but good to know it exists.
Look, we can talk about this all day, but the single best way to really get these trade-offs is to get your hands dirty. Seriously, try implementing all three on the same dataset. You will immediately feel the difference. The elegance of the Fennec tree, the raw power of the segment tree, and that insane speed of the sparse table. So, now that you know the trade-offs, what's the big takeaway? It's that there's no single best tool. There's only the right tool for the job. It always comes down to that fundamental trade-off in computer science: speed versus flexibility versus memory. So I'll leave you with this question. For your next technical interview, which of these structures are you going to master first?